All right. All right. So let's move on to the main subject matter, the impossible mainstream gravitational model. And the reason that I'm doing this, guys, is we talked a little bit about this on Friday in the Journalism Lounge. And one of the things that I think Austin and I both take great exception with is that, it is the inclination of many flat earthers to dismiss in its entirety the idea that gravity even exists at all. Now, there's a lot of controversy on the definition of what gravity is. I would prefer to call it an acceleration that is earthward. It's something that I think is frankly undeniable. A lot of people say that that is not necessary to have any type of force or acceleration to cause things to go to Earth, which to me is very non sequitur, doesn't make any sense at all, because things fall down. They don't go up, they don't go sideways. There's something that determines up from down. And really, that's what this whole debate kind of centers around. Now, the reason I believe that flat earthers have the stigma against gravity is because of the way that it has been misapplied to things that are going on allegedly in space. The ISS being slung around the Earth at 17,500 miles an hour, the moon being slung around the Earth at whatever speed it is, the Earth being slung around the sun, and all the other planets being slung around the sun. That is when it gets into the absolute absurd. And what I'm going to show today is that mainstream really has nothing to base this on. Mainstream gives us mathematical equations that honestly, straight up, are based more on electrical equations, which are frankly identical to electric force equations, and try to apply these equations towards objects in outer space using the gravitational force, which, quite frankly, even admitted by the mainstream, is 10 to the negative 37th or 10 to the 37th times weaker than the so-called equivalent static or electric force, right? Also, the gravitational force is supposedly has to obey the inverse square law, just like magnetism and any type of EM radiation or anything like that. Well, when you start thinking about that, about the utter and complete total weakness of this field, and think that it diminishes on a basis that is proportional to the inverse square law. And of course, we've done a lot of things with the inverse square law, like the moon, which is, something like 14 quadrillion times brighter at the moon surface, supposedly, according to the inverse square law, than it is here at 1 lux or 1 lumen on Earth. Obviously, you can see the scale of what we're dealing here, and also the scale of the deception that's going on behind it. So, Austin and I and Ken Wheeler and many other people have talked about the idea that gravitational forces are more akin to something that would be like an incoherent magnetic field. Zach, Good Times for All, has made some beautiful videos on that. We have been consulted by a PhD electrical engineer that gives us this information and has guided us through looking at this, which is great. There are debates going on. Gravity is nothing but an incoherent magnetic field distribution. Things like this are very interesting. Ultimately, by the way, the guy that's promoting it as an incoherent magnetic field wins the debate. This is something that will be in the show notes. But I mean, to say that it's not being talked about would be absolutely untrue. A lot of people are on board with this idea. The other thing that we've discovered about incoherent magnetic fields is that as you increase the incoherency of the field, or add more and more magnets to the mass, if you will, that rather than increase the magnetic pole or the electrostatic pole, it decreases. This is something that is shown experimentally to be a fact. So the mainstream notion that the more mass an object has, the more gravitational pull it exhibits is absolutely false, and they have absolutely nothing to demonstrate that as being true, other than their reference to the Earth. And we're about ready to tear that a new one here very shortly. But what's most interesting about it, like I said, is all the equations that they use to prove their alleged gravitational model and a gravitational field. Ironically, is the equations are exactly the same as they would be used for electrostatic models. Okay, this is really, really super interesting. And where was that? Let me see if I can find that. It doesn't matter. All right. Oh, well, here we have the similarities of forces. From looking at the two force equations, you can see the similarities in how gravitational force can be considered parallel to the force between two charges, right? And like I said, the equations are virtually identical.
So it's all some metaphors going on between electrostatic, electric, and gravitation that's going on there.
Exactly. And
right.
It's all to cause confusion, right, about what's actually happening. The irony is even when they compute these things, as we're going to see here very shortly, they will compute it and use the gravitational forces measured out in newtons. And what's ironic is when you convert newtons to electron volts or anything like that, you get absolute numbers that should be able to be measured. But you know what? They're not. They can't measure any so-called gravitational field, so what they have to resort to is things like LIGO, which is another complete farce that is saying that, well, when a gravitational wave, the way that they can measure this field is when it goes through, a tunnel, a 4-kilometer tunnel, and it physically shortens it by 1/1000th the width of a proton. All of a sudden, that's proof of gravity. It's like, guys, you got to be kidding me. They tell us that our atmosphere is held on to the Earth, right? Supposedly by this gravitational pull. Well, great. So even if that was true, just say even if that was true, what's happening is by the time you get up to 300,000 feet, the atmosphere is so thin, right, that there's virtually nothing there. So you would think that if the gravitational force was so strong that it wouldn't even make it that high, right? It would all be highly concentrated right next to the ground, right? But instead, what they will tell us is that gravitational force, even though it can't seem to pull all of that stuff out of the upper levels of our atmosphere, it still has enough power, even being subject to the inverse square law, to be able to hurl the moon and the space station and anything else around it caught in this gravitational lasso. It's
but
absolutely...
that doesn't make any sense, right? The inverse square law. How can it hold the moon, which is very far away, if the inverse square law then should be saying that it should hold us much stronger to the ground, right? And it doesn't.
Exactly. Same with the sun. Same with the sun. How is the sun slinging around planets that are, a couple billion miles away? How is it capturing them and holding it in this gravitational field? And all the time, all the while, ladies and gentlemen, we cannot measure this field. There is no field to measure. Now, when you deal with electrostatics or electromagnetics, you can measure the field in Teslas. You can measure the field in electron volts. It is absolutely there. But when we're talking about gravity, brother, there is nothing there that can be measured, period. Right? So and why do they do all of their math and computations if it was not, in fact, based on electricity? That's the great mystery, right? So
they measure things falling, right? They have those things that they do that, right? But it's some sort of inference, right? It's a different thing that's going on. It's not the actual thing that's doing it, right? It's something falling
precisely.
and then going backward toward it. And I was going to ask you, like, the scale, the inverse square law, when you talk about the moon, when you get those like crazy number of lumens, that's computing the mainstream distance, right?
Yes, that's computing. There's two things. Ben, when he did his, he did it at 1 lux. I took the Wikipedia figured, which gives the mainstream the benefit of the doubt at 0.1 lux. Or 1/10 of a lux, and you compute it backwards, and by the time you get to the surface of the moon, it is literally 14 point something quadrillion lumens. There is nothing that is that bright that we can even imagine. It's just...
So the distance is wrong, right?
The distance, everything about it is wrong.
Right.
You know, take your pick, right?
But do you think it would work like with the inverse square law, were the distance much shorter? You wouldn't get to those crazy lumens. It would be more reasonable or not?
It would be somewhat more reasonable, but then again, you know, you'd have to bring it way, 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 way closer. You know, maybe a couple thousand miles. Gee, isn't that a coincidence? You know, and we could certainly do the math and you know, backward engineer it. That wouldn't be difficult. But even then, you know, we're talking about something that when the astronauts were supposedly standing on the surface of the moon, if they would have been exposed to 14 quadrillion lumens of light, it would have vaporized them. I mean, period. Would have vaporized them, right? There's just no way that that could possibly happen. So again, the gravitational so-called field, which is not a field at all because it can't be measured, and they have to go, you know, like I've said a million times, in order to prove the so-called gravitational field, they have to go to an event that happened a long time ago in a galaxy far, far away, where, you know, 450 million light years back, there were two neutron stars that collided, two black holes, whatever, and, you know, the collision of these two things created this gravitational wave that was sent out over the cosmos for, you know, hundreds and hundreds and hundreds of years, that arrives on Earth. And even though it supposedly has, you know, orders of magnitude more gravitational strength than the moon, which of course is lifting up trillions of tons of oceans, nothing happened. You would have thought that all hell would have broken loose, right? Being hit by a gravitational wave like that. Was there? No, not a damn thing happened, right? Mm-hmm. And again, I've said it before. Why doesn't LIGO pick up the gravitational field from the moon? Why? Right. Because there isn't one. Okay? All right, so what we're going to do is I'm going to play a latest video by Zach, Good Times for All. As you know, Zach has been staying with us for quite some time, and it's great. So getting him a computer was one of the best things that I ever did because he's turned into quite a really good video maker. And I'm going to play this one. It's only 1 minute and 40 seconds, but what he's going to do is he's going to show an MIT professor, who we all know who he is, Walter Lewin, and Walter Lewin is essentially saying, hey, you know what? What's holding everything together right down here is the force of electricity. And he says it's only when you get out to the stars that things are taken over by gravity. And of course, this is completely unproven. We don't know any of this, and we have no evidence whatsoever, but it's in the curriculum,
Magic
so he has
happens.
to teach it. Yeah.
It's amazing.
So let's give Zach a listen here and on this video on Walter Lewin, and let you guys decide. Here we go, guys.
Hello, everybody out there in YouTube land. This is Good Times for All, or Zachary Zabala here if you prefer. In this video, we're going to ask a question. Does this MIT professor confirm electric gravity?
I wonder what the hell holds the nucleus together? If there is such a tremendous force on these protons, well, what is holding them together are the nuclear forces, which we do not fully understand, but thank goodness the nuclear forces are not part of 802, so I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together.
Okay, and one thing Zach wanted me to show was, and he's going to remake this video, and he's going to put this part into it where he essentially says right after it that, well, here, let me just play it. Here we go.
15 meters, and you calculate this ratio, you will find that it is 26 orders of magnitude higher than the gravitational acceleration on Earth. 26 orders of magnitude higher. So you wonder what the hell holds the nucleus together? If there is such a tremendous force on these protons, well, what is holding them together are the nuclear forces, which we do not fully understand, but thank goodness the nuclear forces are not part of 802, so I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together. And now you may say, that's very inconsistent with what you just told us, because didn't you tell us that D cancels if you compare gravity with electricity?
Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass.
Okay, so basically, you know, what Zach wanted me to point out there was the inconsistency of the arguments that even Walter Lewin himself and the mainstream have to address when it comes to gravitational versus electrodynamic type of forces, right? Again, there is absolutely no field to measure. You know, the only thing they can do with gravity is describe what it does. What does it do? Well, it accelerates things at approximately 9.8 meters per second squared towards the Earth. All right, great. So, and again, like I said, you look
What
at...
about dark energy and all this, Bob? Like, how does is it not supposed to supplant gravity and do also some pulling of its own?
Yes, that was the entire reason why dark energy was introduced, is because of the fact that they know full well that gravitational forces could not possibly slingshot Earth around the sun or the Milky Way around the center of the galaxy, the great attractor. It cannot happen. It simply does not have the force required to do so. I think this is also another reason why they came out with the incredibly stupid model of bendy space-time, right? Again, it's just obfuscating the entire issue that people are questioning this, so they have to come up with something that's even more absurd that people cannot possibly understand and obfuscate that. But like I said, here you have it. When you look at the gravitational and electrostatic forces and the equations that govern them, they are virtually identical, right? So, and yet you can actually measure electrostatic forces. They're actually measurable. You can measure electromagnetic forces. They're absolutely measurable. When Austin and I talk about dielectric acceleration, like what Ken Wheeler talks about, when you're talking about dielectricity, we're talking about a composite of magnetic and electrical energy, right? And we know experimentally that if you make any electrostatic energy incoherent, it becomes weaker. If you make any magnetic energy incoherent, it becomes weaker. So why in the world, you know, based with everything being all the same, they could make the ridiculous assertion that when you increase your mass, you're actually increasing gravitational attraction? That's absurd, right? Sorry, doesn't work. What we do
Bob,
know...
Can you explain a little bit just the difference between the electric and the magnetic? And or the similarities, or whether is it different at all?
Well, the electrostatic forces are obviously in the realm of electricity, and they are very complementary to one another. So, in other words, they're kind of two heads, or in Ken Wheeler's case, he describes gravity, electrostatics, and magnetics as three heads of the same hydra. But let's just look at magnetics and electrostatics, right? When you have a magnetic field and you take and you cut that magnetic field across a conductor, what will happen is it will induce an electrical current flow in it, okay? Mm-hmm. Conversely, if you have an electrical current that is propagating through a conductor, around that electrical conductor, that coaxial circuit, if you will, it will generate a magnetic field. So they are two, you cannot have one without the other, right? Now,
that's what I was thinking, yeah. That we treat them almost separately for some reason, which is another one of those ways in which terminology gets in the way.
Right. Well, they're essentially the same thing. They're the same type of energy. They're this dielectric energy or this etheric manipulation, but they are in different modalities, right? Um, Meaning, it's kind of like when you have ice, you have water. You have water in a state where it's liquid. You have water in a state of ice where it's a solid, or you have water in the state of steam where it's a gas. Or it's all just water. It's simply water in a different modality. So apply this to electrostatics, electromagnetics, and this supposed gravitational force, which nobody is denying that there is a downward acceleration. But what is causing that? It isn't this completely new and unproven thing called gravity. It is a product of electricity and magnetism. The only reason that we are even allowing it to be called gravity is because it does, in fact, create an acceleration towards the Earth. This is undeniable, right?
But it depends on some few things, right, Bob? Like some things go up, and then some people obviously point that out. Not sure it's an elephant in the room, but they'll say, yeah, helium goes up, and or underwater you go up instead of going down, and things like that need to be accounted for.
I totally agree, and and that's some of the things that I've kind of addressed on the Jeranism Lounge is the question that I asked my friend, the PhD electrical engineer. I gave him the whole spiel about helium, and isn't it interesting that the mainstream explanation for it is this buoyancy, it's more buoyant. But my point was, again, and I want people to really think about this, is that if you have two balloons and they're not blown up at all, you drop them, they both fall to the ground at the same time. If you blow them both up with air, let them go, well, they kind of float down to the ground because there's an element of buoyancy going on there. Now, if you take helium and you take an empty metal container and you fill it up with helium, guess what? The weight of that container actually increases, right? Why? Because helium has mass. Helium has weight, but when you put it inside of a balloon and you blow it up to an identical volume on the outside, the helium goes up and the air will still go down. Well, why is that? Well, again, the mainstream is saying that this is a product of it being more buoyant. I've looked at other possibilities in that helium and hydrogen are both diamagnetic, and they are essentially repulsed by electromagnetic fields. Am I right? I don't know. But it
so
just
I suspect it makes sense for me. I don't know what you guys think.
Yeah,
Bob,
exactly.
would you agree that a big distinction that I think a lot of people kind of conflate is the difference in little g and big G, which is essentially what that professor's explaining. Little g is the local acceleration on Earth that we see, and we're just trying to properly define it. And then they have a little fantasy force that they've come up with on the side to explain space. Would you agree with that?
Yeah, I would say that's reasonable.
Right, so that's just kind of how I see it. I don't think downward acceleration is obviously inevitable, and then I agree with exactly what you're saying. It's got an electrostatic component, and then that's what that professor's like conceding that, right? The downward acceleration seems to be electric, but when we get into la land, then there's this other force, and so I think that's kind of why people freak out. They're like, I've been trying so long to dismantle this nonsense gravity that they don't want anything to do with it, and they don't understand the distinction,
Exactly. And like I said, my problem with that is, there are people going around in this community saying gravity, this acceleration doesn't exist. Everything is explained by relative density. Even going so far as to claim that relative density is a force. That is the dumbest thing I have ever heard in my life. That is simply not true. Accelerometers or gravimeters actually prove that, and I can safely say that because these high dollar test equipments, which are based on laser interferometry, will show different acceleration rates at different places on the Earth. Again, is it this mystical gravity that appears that is only claimed by science to exist, or is it caused by the electromagnetic / electrostatic / dielectric acceleration that Ken Wheeler talks about, that you and I have talked about, Austin? It seems to me that when you're talking about dielectricity, magnetism and electricity, that's something that is absolutely measurable. That's something that is absolutely provable. And it's also something that we can apply towards objects, and we can either levitate them, we can either repulse them, or we can attract them. Why? Because everything in the universe has an electrical charge potential to it. So it only makes sense.
One question, Bob.
Yes.
If you talk about repulsion, how fast can you accelerate if have people try to accelerate things by just repelling them electromagnetically?
Well, that would be proportional to the force applied to it. Like a rail gun, for example. If you accelerate a projectile with a rail gun, it'll kick something up to, God, what is it, 3 miles a second? It's a ridiculous speed. But
and it's just magnetic repulsion.
Exactly. It's a columnated magnetic type of propulsion that obviously is directly proportional to the amount of Tesla magnetic fields that they are putting towards it, as well as the coherency, as it's being fired down that rail, right? So it is directly proportional to the amount of energy that's being put into it.
How fast you say?
I think they're up to like 3 miles a second, something like that. I may be wrong on that, but I can tell you this: it's faster than all get out, and they can hit a target over 100 miles away. So yeah, somebody could actually look that up. I may be wrong at 3 miles a second. Whatever it is, it's really, really fast. Okay.
Bob, let me ask you this, just see what you say. If there was a universal down, so that is a given. Let's say there is a basement of the universe. Could relative density then be a force?
No, relative density still would not be a force. However, relative density, after that bias is set, and I've said this since day one, relative density absolutely then determines the ordering of things. But you still have to have that initial bias. There must be a down.
So I'm saying if there is a universal down, there is a basement of the universe. So just like there's some things that we just have to accept are the way they are. So let's just say there is a universal down. Then couldn't relative density be a force itself? If not, why not?
I wouldn't say so, because relative density is nothing more than that. It is the difference of mass density from one material to another. That does not constitute itself as a force. There has to be something externally acting upon it.
Together with the density, Bob, isn't there also some level of electro repulsion or something like that that we describe as density? Like, say, hydrophobic, how oil separate from water. Is it just density, or is there something else to it that's electromagnetic as well?
Honestly, I don't know. I would say there's a possibility of that, but I think density is the best explanation for it, buoyancy and density. Mm-hmm. And like I said, I have nothing against the buoyancy and density argument. They are absolutely valid, but they simply are not a force. There's something, just like the Vomit Comet demonstration. If you take away that downward acceleration by essentially zeroing out the g, then the liquids do not want to mix. But if you continue pushing that plane over where it pushes things to the ceiling, what will then happen is those liquids will order in the opposite direction. And to me, that's pretty conclusive, telling you that there has got to be a bias there in the first place, something that is absolutely determining up from down. And
that'll be right, but the density also becomes apparent with that little experiment there.
Very much so. But what I'm saying, and what Austin I'm sure is saying, is we're saying that it is not this thing called gravity in as far as the way the mainstream is defining it, right? Gravity, quote unquote, is an electrical / magnetic or dielectric type of acceleration. Ken Wheeler says this, and again, dielectricity and magnetism and electricity is something we can actually measure. We can actually get a field strength from it. You cannot get that from so-called gravity. It doesn't exist. That's why they have to come out with these retarded things like, oh, well, gravitational waves pass through something. They shrink the size. They shrink by the size of a 10,000th or a thousandth of a proton. That is absurd. They do the math for electricity. They do the math for magnetism. It's the exact same equations. For God's sakes, why don't they just admit it's an electrical force, right?
Do you want to hear something interesting, which is the quote that I found in this History of Science book? I think you're gonna think this is interesting.
Okay.
I think it's a good segue into it. Okay, so they're talking about, basically what he's talking about is scientific paradigm shifts and how they change your perspective. Kind of like goggles, actually. He uses even the metaphor, but then he goes through many different so-called scientific revolutions, how it changes the set of problems that people are focusing on. He says that, scientists, they're trained to be puzzle solvers and not paradigm testers. That is one of the things he says. But then when it comes to Newton, he gives an example here. Or again, Newton wrote that Galileo had discovered that the constant force of gravity produces a motion proportional to the square of the time. In fact, Galileo's kinematic theorem does take that form when embedded in the matrix of Newton's own dynamical concepts. But Galileo said nothing of the sort. His discussion of falling bodies rarely alludes to forces, much less to a uniform gravitational force that causes bodies to fall. By crediting to Galileo the answer to a question that Galileo's paradigms did not permit to be asked, Newton's account hides the effect of a small but revolutionary reformulation in the questions the scientists asked about motion, as well as in the answers they felt able to accept.
Interesting.
From my understanding, Newton didn't even really postulate a definitive explanation. And then kind of like touching on what Jaren's saying, the way that I understand it, at least, is I'm just like kind of trying my best to understand what the fatherheads of the electrical field theory thought of gravity as just an effect. And then the only force, if you will, would be the magnetism, because it's a field. But the gravity is just an effect, and then the density is a factor into what the effect is going to be. But it isn't actually causing it, and then there's just the natural absolute frame of reference, and something falls, and then because it is electrostatic, it's an electrostatic, or more specifically dielectric acceleration, and the gravity is just an effect that's negligible, and it's electrical. That's at least the way I understand it.
You guys are way beyond the Newtonian paradigm by now. The way you talk about it, gravity that he was talking about is very, very, very different, right? And this is one of the point here of what I just read is that, someone comes up with an idea that they think is universal, and then they can look back at the works of others and say, oh, here, he proved me right. And then they go on to make different claims, right? And then the people that follow that tradition then start applying the same set of problems to solve the same kind of theory, right? And that can get passed along as a tradition. That has nothing to do with the actual nature of things, right? In this case, there's a Newton having no idea, no sense of electrostatic, and that would come later for people. But still, the idea here that gravity somehow survived, and he talks about it here as well, like that there's these heroes of science that they, line up one after the other as if there's this natural, easy progression from one finding to another. Whereas, in fact, when you start reading what they're saying, you get much more gray areas. It is much more complicated, and it's not so simple as the textbooks. And this is the main point of this book here, is the centrality of textbooks, textbook writing, and how they basically formulate everything for the trainee. And then there's a bunch of other problems, but that's what holds back science, like the lack of historical knowledge of the scientific process itself, so-called scientific process, right? These changes in so-called paradigm shifts that we have now, but the history itself is key to uncovering,
I absolutely agree, Rodrigo. And, that's just like the Michelson-Gale, Michelson-Morley, understanding the true nature of those experiments, and the Sanyak, bringing forth the truth of the ether, right? And let's just cut to the chase here and talk about what's really going on here. And Ken Wheeler is nuts on when he says this. It's all about pressure mediation, right? That's what's going on. That's what gravity is. That's what electricity is. That's what magnetism is. It's all about this pressure mediation, right? So
Exactly.
what's interesting is that the mainstream, for whatever reason, and I
How
think
does that work? What does that mean exactly, the pressure mediation?
well, it's basically a balancing of forces. And when you cause a disequilibrium in forces, right? Specifically the ether in this case, and of course we talked about the ether and how, at least in my view, and I think in several other people's view also, the literal nature of matter is a cymatic manipulation of the ether. Specific on specific frequencies. Of course, you can tie this biblically to the Word of God, right? The complexity of these sound vibrations, so to speak, of God's voice, manipulating the ether and literally manifesting form. And it is amazing when you look at cymatics, what kind of forms can be manifested just by mixing up a few different vibrations, right?
I think you're talking about those experiments with different kind of shape things that like are chocolate or whatever that they start almost looks like creatures. Yeah.
Exactly. And think about this for a second. What's happening cymatically there, right? You're vibrating these like Lyco powder and things like this, and what's happening is you're mediating the pressure. You're causing different pressure formations around that Lyco powder, which is giving it form. Same thing with the ether. This is what pressure mediation is in the grand scheme of things, as far as cymatic creation through the ether. Okay, my opinion, but
interesting.
I agree with that, Bob.
Good.
I've been out for a while. Sorry.
Okay.
And I just wanted to throw in there a sonoluminescence with the lights in the sky. A lot of people, myself included, think that's an interesting theory as for the explanation of the lights in the sky, because of sonoluminescence through water. You can replicate basically what they call a star in a jar, and I'm sure you've covered it a number of times before. But with waters, you can create a plasma point, and that's basically through pressure, as I understand it as well.
Yes, it's just like Tesla said from the get-go. When you're looking at the nature of the universe, think in terms of frequency and vibration. Yeah. No truer words were spoken, folks.
Would you say, Bob, that sonoluminescence is quite similar in a different level to this kind of cymatic mediation that we see with the other pastes and so on?
Absolutely. It's the very same thing. The sonoluminescence essentially is caused by this cavitation of a liquid, right, which causes specific pressure points. Again, we're going back to this pressure mediation, right, which is causing a fluorescing or a luminescence of the water. So again, it flies in the ether, it flies in cymatics in Lyco powder, and it certainly seems to make sense that it would behave the same way with the luminiferous ether. And the voice of God, if you will, speaking things into literal form or literal creation. It just makes sense to me.
Does the sonoluminescence itself, does it have voltage in it? What is it doing? Is it creating a magnetic field of its own as well? Do you know about this?
I would assume that it must. I mean, I don't have the specifics on it, but we know that it generates light, and light, is a form of electromagnetism. And what do we know about electromagnetism and electricity? It goes back to the same thing. Where there's magnetism, there's electricity. They are two heads of the same hydra. So, and
from the perspective of light, which is more of my area of expertise, the light produced from the star in a jar, the sonoluminescence, is the same characteristic light that you get from the similar thing produced via electricity in the case of like an electric arc lamp, which is the first light that was ever made in supposedly the early 1800s, I think around 1828, I think they were doing them in laboratories, according to the historical narrative. These old street lamps that they had around the time of the advent of photography, those are electric arc lamps, and they produce a spectrum that is equivalent to the star in the jar that if you do in your home laboratory, you need to protect as you would a welder's arc, because again, it's about the same exact profile of light. There's a lot of UV in there, and it's the broad spectrum radiation.
Exactly, UAP. And another way to look at that is, when I was 16, I used to work at a drive-in theater, right? I worked in the snack bar, but we got to go up to the projection room, and this may still be this way today, I don't know. But when we went up to the projection room and looked at the projectors, what they had was two carbon rods that they put a voltage through together, and then it would create this spectacular arc, super bright light, and that's what provided the light source to project onto the drive-in theater. Same thing if you think about a modern day arc welder, right? What are they doing? I mean, when they're welding and they're generating this unbelievable amount of light, it's because of arcing electricity. Same thing.
Yeah, and it'll sunburn you. It'll kill all the germs around, and it's extremely bright, like looking into the sun, right? Those are very durable lights, and you can find them around still. The projectors, those are the carbon rods. They're about, what were they, like a 1/4 inch apart, the rods?
Yep.
And they just had an arc, and it puts out a lot of heat, maybe a little bit of smoke even.
But a lot of light.
Extremely bright.
Yes.
Yeah.
Exactly. So, again, that's what I'm saying. All of this seems to be a product of electricity and magnetism, something we can measure, something we can manipulate, something that we seem to have full control of, or at least a big amount of control of. And they want to attribute these forces, these accelerations, to something that simply is fabricated. I mean, the gravity that they say is something different. I mean, a lot of people, they will try and tell you that gravity is not magnetism, it is not electricity, and yet they will, like, I'm about to play this video, which is unbelievable the way they describe this, but again, that's all we can measure, that's all we can actually do. And when you take the electrical and magnetism calculations, they are applying them exactly the same way to this gravitational field, except they will then turn right around in the same breath and say, well, it's 10 to the 37th times weaker. Well, then how in the hell does it get anything done? That's why the guys at the Thunderbolts Project are saying, no, the universe as it is, and granted, they're still in some sort of a heliocentric model, they're saying that there is no way that gravity could possibly do this. Even the mainstream admits it. That's why they have to admit stupid stuff like dark matter, et cetera, et cetera, et cetera. So now the electric universe...
Can I add to that?
Oh, sure. Go ahead.
Well, just to give everybody an idea of how weak of a force this is, you hear a lot about the Cavendish experiment. And when I had a little back and forth with Scott Manley in emails about the nature of gravity, and he was citing the Cavendish experiment, which I researched and found that it was meant to be a proof of concept experiment, like a demonstration for somebody else to take the lead and replicate and reproduce, which I didn't believe had been done to any satisfaction. But then he produced some studies that were peer-reviewed and accepted, which I read. It was very tedious reading, and the kinds of assumptions that had to be made to allow for them to, in my view, back their way into the gravitational constant that had been agreed upon by committee over the years. I forgot the name of the society that meets. There's so much made of like this flat Earth society. Well, okay, that's not a real society. The real societies are the ones that meet and decide, okay, the big G, the gravitational constant, the OG of gravity, the original gangster number of gravity that they agreed upon, that happened by committee. And it's adjusted a little bit over the years, supposedly based on accuracy, but it's just them taking a bunch of experiments that do not have overlapping results of accuracy, of precision rather. The accuracy.
How can something be a constant that has different measurements? Like Bob was pointing
Exactly.
out, gravimetry, you find different anomalies. How can it be a constant?
Exactly. That's why they had to meet and have the committee and basically it's like getting together before you get questioned separately by the cops. This is our story. Okay, this is G, this number. Back your way into it, and you get an award, or you get your experiment peer review gold, green stamped, gold starred even.
And I'm sorry, UIP. I was just going to say, and one thing that I want everybody to realize is when they start looking into these so-called gravitational anomalies, there's all kinds of places around the world where, gravity is kind of wonky, right? Things like cars will roll uphill instead of down. And of course the gravimeters will measure dramatically different accelerations at this point. And I will say this for the record, when you look into this, that every one of these sites also has, coincidentally, I don't think so, a magnetic anomaly that is directly associated with it.
Right, like an iron deposit or something like that. Yeah, they have those mapped out. Is that what you mean? Like those gravity maps?
Yes, and the magnetic field in those areas is just as anomalous. Gee, that would almost indicate that, wow, somehow they're tied together.
Yep, exactly. And so they say this is where they get into this whole discussion of gravity. Oftentimes I see them talk about frames of reference, and that is like a Jedi waving his hand and saying, you only need to consider this and not these other things, which is so unscientific. Well, they talk about the Cavendish experiment, and they talk about the frames of reference eliminating everything except the two metal balls hanging, and how do they swing together or rotate around, that type of thing. To give you an idea, when I really looked into these studies and spent hours and hours reading the fine print and everything else with the assumptions, to give everybody an idea of how weak the gravity force is, they talked about light pressure. And what I mean by that is the light in the room during the experiment, to them, in their view, exerted a pressure on the objects being tested that affected their position. So, so like you turn on your fluorescent lights and it pushes on the object that they're measuring. That's the level of variable that they're dealing with, that they're claiming they've accounted for all of it. And it's just a little bit crazy to measure a force that's that weak, and then to go on the other hand and say it's slinging around, slingshotting planets and satellites and everything else.
And that's the whole trick. It's not, they're not measuring a force. They're measuring the behavior of something, the characteristics, the attributes of it. In other words, if I take a pen and I drop it to the table, I'm not measuring any force. What I'm doing is I'm observing, and I'm applying mathematics to what I'm observing. It's not measuring anything. It's observing and applying the appropriate mathematical equations to describe what's happening. There is no force to measure.
And the description doesn't work out mathematically, and that's why they had to introduce the dark matter, where you end up having the best mouthpiece being Neil deGrasse Tyson on some show explaining that there could be gravity spilling out from another universe in the multiverse. That's their explanation for it. It's just it's absurd. And if you haven't thrown your papers down and kicked your desk over and walked out by then you never will.
Exactly.
Isn't it ironic how they have this light pressure, and the sun doesn't exert light pressure on the Earth, and then it has gravity instead?
Well,
this experiment.
It's not in the frame of reference, so they don't. Because they
Right.
haven't really solved the three-body problem. You know, you have the Earth, the Moon, and the Sun, and the Moon's going to slingshot the Earth. You're going to feel yourself, okay, are we in the, just like, instead of just like the tides or something, you would be saying, well, are we going faster today around the Sun, or are we slowing down? And it's not observable in any way because they haven't observed it, but then they say, well, it's not within the frame of reference. It's negligible because of the differences in mass, but it's not. If the Moon weighs as much as the Earth and the Sun, then these effects would be seen. But yeah, even light pressure on the scale, on the scale of the entire half of the Earth that would be measurable, I would think it would be significant enough. But to my knowledge, it's never been quantified.
Yeah, exactly. So
This all reminds me of I don't know if you guys remember a video I did about a year ago called "Cosmology Has Some Big Problems."
mhm.
Who remembers that? It was a Scientific American article, but everything that we're talking
Yeah.
about was covered
Mhm.
really extensively in that article by somebody who's even in their own world, who explains
right.
how everything is basically ad hoc to explain something that's fundamentally wrong. And this is somebody in their own line of research that it can admit why we have dark energy, can admit why we have dark matter, can admit why none of these things have any empirical evidence whatsoever. And yet it's all just to basically, fill some mathematical unification and to make the science seem complete. But it's not. It's got so many errors, but you can always with math add something else. You can
Yes.
always just rework the formulas. So anyway, people should check that out. Maybe I'll re-release it because it was good. I don't remember when that was posted, probably about a year ago.
Yeah, it was a great video. Yeah, absolutely.
Yeah,
You should
and then-
release it.
What they did, I'm not sure if it was right after that, Jaron, but like I think it was about 2 years ago when they came out with their LIGO results, where supposedly this is experimentally proven some of the claims that Einstein made over 100 years ago.
Yep.
And it's another example of something that is billions of dollars, that's off limits, it's underground, it's huge. You're supposed to just accept that experiment, but it falls into that category of everything else that they've used for their experimental evidence. There isn't. It's not something that is actually
what about, like,
something we
the-
can reproduce.
What about the retrograde motions of some of the lights that we see, like Mars and so on? Would it be explained in the Ptolemaic way? And then would that be magnetic then?
Yeah, the answer to that, Rodrigo, is absolutely not. In fact, all they're doing, again, by the observation of those lights, they cannot solve even a three-body problem. So to assume that they could take all those planetary motions and all the beautiful, geometric patterns that they form and how they're interacting with each other, they can't not even describe it mathematically, let alone solve it. In other words, they're just trying to make you think like they can do that and that gravity magically does all this. We don't know what those lights are other than they're lights, but are they terra firma? Not a chance, in my opinion. And so, yeah, again, but they have to incorporate this as part of their lie, part of their fantasy, and bring it about. So before we get much further, guys, what I want to do is I want to play this video by Bozeman Science, and I want you guys to pay attention to Poindexter here when he's talking about this gravitational field. Well, there is no field, guys. There's no field of gravity. There is nothing to be measured in that field. Again, the only thing they're doing is they're taking a description and applying a mathematics to a description of something that is observed. They are not measuring a field. There is no field to measure. Versus, if I want to measure a magnetic field, I can do that. You can do that with your phone. If I want to measure a static field, electrostatic field, I can do that. That's real. That's tangible. It's manipulable. And, this so-called gravitational field is not real. It's contrived, and it's brought about by observing something that is caused by dielectric inertial acceleration. But just listen to how they obfuscate this and make you think that this field is something that is actually tangible when it flat out is not. Here we go. Oh, and by the way, this is being used for educational purposes under fair use, for critique, commentary, education, yada, yada, yada. Okay, here we go.
Hi, it's Mr. Anderson, and this is AP Physics Essentials 25. It's on gravitational field strength, which is a measure of the gravitational force placed on an object that's in a gravitational field. And so you know that the moon orbits around the Earth and stays there because of this gravitational field. And so if we place it in orbit, watch how the force on those two objects remains constant. The gravitational field strength is the same. But if we were to play around with this PHET simulation, if we move the moon closer to the Earth, you can see the force is increasing. It has greater strength. And as we move it away, it becomes less. How else could we change the gravitational field strength? Well, we could increase the mass of the moon. It's a greater force. We could increase the mass of the Earth as well, and there's going to be a greater gravitational field strength, and it's going to have catastrophic consequences when we put it in orbit. And so remember, any object that has mass is going to generate a gravitational field. And those field lines are going to point to the center of that object. And so any object, and we'll just deal with spherical objects in AP Physics 1, is going to have a gravitational field that's going to become greater the closer we come to that object. And so if you want to calculate the gravitational field strength, this equation works. And it was developed by Sir Isaac Newton. And it really only has those two things that we saw in that video. It's the mass of the object and then the radius, or the distance between that object and a point. Now you might say there's three things in this equation. The first one is a gravitational constant. We lots of times refer to that as big G. But the other two things that are going to affect the gravitational field strength are the mass of the object and then the radius, or the distance from the object. And so in this class, you should be able to calculate the gravitational field strength of an object or sitting on the surface of a really large object like the planet. And so gravitational field strength, this is our equation right here. There are three parts to it. And so if we're measuring the gravitational field strength at a point separated from that object, we need to know the mass of the object. We need to know the radius. And note this, that when we're looking at the radius, it's not from the surface of the object, it's from the center of mass of both objects. In this case, one is just a point. And then the last one is going to be the gravitational constant, or big G, and that's just 6.67 times 10 to the negative 11th. And then we got a bunch of units coming in after that. And so let me give you an example problem. Let's say I want you to figure out the gravitational field strength of a baseball. You could imagine it's going to be really, really small. There's not much mass in it. But if you want to solve this problem, I haven't given you enough information. You need to know what's the mass of that object. It's 0.145 kilograms. And you also have to know how far away is it. And let's say it's 2.0 meters. And so you maybe have forgotten what big G is, so we'll put that right up there. 6.67 times 10 to the negative 11th. And so you may want to pause the video right now and try to solve this problem. Or you could just watch me do it. I'm going to take those three values and I'm going to place them into my equation. So I'm taking the big G times the mass divided by the radius squared. And so when I solve that, I get a gravitational field strength, or a G, of 2.4 times 10 to the negative 12 newtons per kilogram.
All right. So I want to stop it right there because I want to point out something that Poindexter here is saying about these field strengths, right? So he does the math and he comes up with 2.4 times 10 to the negative 12 newtons per kilogram. Okay, so what they're doing then is they're actually applying things that should be measurable to something that is conceptual, right? Well, if we actually look at that and we say, all right, well, how much energy is in a newton, right? Let's just ask that, okay? So it says 1 newton is the force required to accelerate 1 kilogram of mass at 1 meter per second. The newton meters are termed joules. The joule is named after James Prescott Joule, who first calculated the amount of electrical work needed to produce a unit of heat. All right, great. So let's look at a joule, right? And let's look at some of the conversions that we can make. Let's look at it to a watt hour, right? That is a watt hour, and of course, watt is the equation as P equals IE, power equals currents times voltage. This is a very small value, but it's definitely measurable. Or you can take it as the electron volt. Well, essentially what that is, this figure right here, 6.242 times 10 to the 18th, is also defined as a coulomb or 1 ampere. Right? 1 ampere is defined by this many electrons passing by a certain point in a conductor in 1 second. All right. So 1 ampere is actually quite a bit of power, right? Or quite a bit of, I should say, electrostatic charge, and it's very measurable. So if you were to take this and go back to Poindexter's formula here, right? Then that tells us that we should have a significant amount of charge potential that we can measure in this so-called gravitational field. Well, isn't it interesting that they're using something that is charge potential? And you know what? We can measure charge potential in the air, and that, of course, goes back to the 100 volts per meter of voltage that we can measure going from the Earth ground up. But where is gravity in this? Where is the gravitational field? What they're doing is they're using math, and they are using units that are directly related to electricity and magnetism. There is nothing in here about gravity. This is all complete fantasy. So I just wanted to point that out, and let's hear out the rest of what Poindexter has to say here. But this is just utter nonsense. Here we go.
Bob, one question would be, like the electron, do they conceive of it as a particle or as a current?
They conceive of an electron as a particle. However, if you look at it more in the Walter Russell or Ken Wheeler or Nikola Tesla, it's more of a, I think Austin describes it better, as a sampling of the... Austin, how do you describe it? You describe it better than I do.
Just the terminal end of one unit line of dielectric induction. So it's just like a dielectric line of induction. It's got little gaps in it, and then they quantify the gaps as some physical particle.
Beautiful. Exactly. That's what he said. Thank you, Austin.
Yeah.
All right. So
very interesting. And then what you're saying here is, whereas like gravity should have nothing to do with electric fields or magnetic fields.
Well, they say that, but then they turn around and use the very measurements for electricity. That's the absurd part about it. It's like, really? Where's the gravitational field? Well, you'd have to use a LIGO facility to measure that and watch something decrease by the 1,000th of a width of a proton. Oh my God. Give me a break.
And how easy is it to measure electric stuff? Like it's very simple. You can get a machine that does it right.
You can use your phone to do it. Your phone will do it. Yeah. That's how unbelievably common it actually is. So let's hear out Poindexter here for a couple more minutes, and then we'll cease this nonsense.
Cancel out all those units. We've got newtons on the top. We've got kilograms on the top, but we've got kilograms squared on the bottom, so we're going to end up with 1 kilogram on the top, and then the meter squared are going to cancel out. And so that's going to be the gravitational field strength of the baseball. Incredibly small, but it's still there. Let's say we were to do this. Can you figure out the gravitational field strength of the Earth? So we're sitting on the surface of the Earth. Can you figure out what's the strength of that force pulling you or holding you on the planet? Well, again, you'd need 2 more things. We're going to need to know the mass of the Earth, and it's pretty massive, 5.97 times 10 to the 24th kilograms.
Yeah, okay.
And you also need to know how far are you from the center of the Earth? What's the radius of the Earth? And it's 6.37 times 10 to the 6th meters. And so to solve this problem, you're going to do the same exact thing. We're going to plug it into those equations, those values. And again, it's worth doing, but if you do this, you're going to get a value that you've seen before. The gravitational field strength is going to be 9.81 newtons per kilogram. And so that is going to be the gravitational field strength as we get close to the planet. Again, it's also numerically equal to the acceleration due to gravity on our planet. And you might say it's going to be the same everywhere on our planet, but it's not. If you look at the gravitational field strength on our planet, and this is a NASA image, it's going to vary depending on where you are. Because the Earth isn't consistent, it's not a consistent sphere with consistent density, it's going to have different...
Doesn't that seem to run counter to what they were saying earlier? if the mass is not changing, if the total mass is still the same, then why would the composition or the configuration of that mass make any damn difference at all?
Absolutely. He was talking about the center of it being the important thing, and it was going to be the same. Before he made that point before he had the diagram, right? And now now we have something that doesn't fit it.
That's right. And now on the flat Earth, of course, or whatever, by gravimeters, or gravimeters being these accelerometers measuring differences in acceleration downward, right? We know that these anomalous areas exist. They absolutely do. So what causes them? Well, again, like I said before, when you look at these supposed gravimetrically anomalous areas, what do you have? You have magnetic fields that are also anomalous, and most likely, and I haven't seen anybody actually take a charge measurement in the area, but I would bet the farm that there's also charge anomalies as well. So again,
should those also shift according to how the ether might be moving?
Yes, indeed. That would absolutely stand to reason, because everything is in motion. But their explanation for it is patently absurd. It makes no sense whatsoever. So about 30 more seconds of this, and then we're done with Poindexter.
Differences in latitude and therefore the distance from the center of the Earth. There's going to be geological differences, what the Earth is made up of. And so we can study the gravitational field strength in different areas, and it tells us a lot about what the Earth is actually made of. And so did you learn to calculate the gravitational field strength of an object a certain distance away? And did you figure out how to approximate the gravitational field strength if you're sitting on the surface of a really large object? It's the same equation. It's pretty easy, and I hope that's helpful.
Well, thank you, Poindexter. No, that wasn't helpful at all, except for showing us that your model is full of BS. So anyway, all right. So again, like I said, the calculations, they use the electrical and magnetic calculations. They use electrical and magnetic units of measurement, and yet these have nothing to do with so-called gravity, unless they finally fess up and say the attractive or the acceleration is caused by an electrical force, which they're never going to do that. And that's part of the biggest problem with this. So that,
and then you had the other professors saying that at the micro level it's all electricity, and then at a certain point, where's the transition zone where it becomes gravity, right? Did they talk about that?
Yeah. No, they don't.
Yeah, and Bob, I sent over a couple of things. It's the three-body problem. It's an illustration. So they taught this planetary orbital motion based on gravity, the theory or hypothesis of gravity. And if you see what the results are fed into computers with all of the numbers from Newton and everybody, they just don't work. They don't look like we see planetary motion. And the solutions that they come up with, there's only, well, it's arguable whether they're actual solutions to the quote problem. It's, again, not anything that looks like what we've been taught orbital dynamics should be. And this is just going on their mathematics.
It is very much, though, what we've suspected, and I think what you talked about also before, how the distance between the planets in their model, by shifting throughout the year, should shift all the orbits, which is what you're showing here.
Yeah, and it throws it out of balance, out of whack. It's in three-dimensional space, and over time it just makes a spaghetti diagram, unless you find, okay, these are the supposed solutions. And the one on the left, I'm not clear. It's not clear to me how that's a solution. It doesn't look like anything I've ever been shown as how anything orbits.
Looks like a kindergartner scribbling with a crayon.
Yeah, it's a mess. It's a mess. And this is a three-body problem. It's not a four-body problem or a five-body problem. So whatever their models are, it's just an absolute joke that these equations, the gravitational equation for the main one, could explain what we are seeing. And they can throw in dark energy and and dark matter, but is an absolute. It's just a cop out, really. I guess it just, to me, I don't know if it's supposed to actually address this issue. I think they have some frames of reference explanations, but that's an assumptive basis. It's just another thing to make you walk away from the heliocentric model, in my opinion.
Yep, shaking your head.
What's so funny is when I was a kid, I remember thinking that it didn't make sense that the Earth was being pulled in by the gravitational pull of the sun and the moon was being pulled in by the gravitational pull of the Earth, but of course the sun's is way stronger. And so if you do it, even just, factoring in the proportionate nature, it's like, okay, well, either the moon's going to be going further away from the Earth, or the pull of the Earth is going to be stronger due to the relative distances, and it's going to be getting closer to the Earth, and it would be pretty significant. What are the odds of it being perfect to where we see it there the same? Like, in high school, I remember being like, that doesn't even make sense. And I thought, okay, that seems too simple. I can't ask that question, right?
Right.
Yeah,
Well,
yeah.
And think about this, Austin. By going by their logic, if the sun truly had a strong enough gravitational field to hold the Earth within its boundaries, right, its orbital boundaries around the so-called sun, then you would think that you would weigh not just a little more, but a whole crap ton more at nighttime, right? When you're away from the sun and you've got the entire Earth that's in between you and the sun, right?
Yeah, exactly. And if you play football on one side of the Earth, you're going to be able to throw it across the field effortlessly, and it would be completely different on both sides of the Earth.
Yes, but they, again, what they do, they say, "Oh, no, you flat earthers are dumb. The math says this." It's like, yeah, but you know what? Common sense says something completely different. And again, show me the gravitational field. Show me a measurement of it, not a description of it, of what it does, but show me a measurement of it. I can show you a measurement of a magnetic field. I can show you a measurement of a static, electrostatic field. You show me a measurement of a gravitational field. And you know what? It can't happen because it doesn't exist. Period. And that's what I got to say about that.
Amen.
All right. Cool.
Well, something else is that they added the distances to wash that away, with what you said. Because Austin, when I was a kid, I thought they should hold the Olympics, like the high jump and everything, when the moon's overhead, at noon, and you have all that extra pull, and you can, kiss your fingers and look up and put your hand up to the sky, to the sun and the moon, because they're going to pull you up for that world record. And you go and you do your jump, and it's just epic, Whereas if it were at night or whatever, you'd be like slammed down and, miss your qualifications or whatever. So it's like, no, it doesn't factor in, it's the extremes of the differences in mass and the great distances involved and blah, 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 but it just doesn't hold up. Yeah.
Exactly. And,
Right. They added all those distances to basically like the crazy distances to try to make it unfalsifiable, but it still is falsifiable. Like, even with that, it isn't a sufficient explanation if you really think about it. So, it's just kind of wild world, clown world.
Yeah. So to bring this full circle and back to my original point that I have really, really been trying to get across to people, okay, is that this downward acceleration that is a small bias, just a small bias that determines up from down, that the mainstream calls gravity, right? It exists. Now, if you want to rename all the rest of it something else, that would probably be a good idea. The fact that the mainstream has corrupted it and tried to apply it to all this other stuff is exactly the reason why flat earthers are saying, "Oh, it's horseshit. It doesn't exist at all." But a part of it does exist, and to summarily dismiss this in my opinion, is a mistake. We need to address it on its merits, just like what we did today, showing that, yes, we're not going to deny that there's a downward acceleration that is determining up from down. That much is a foregone conclusion. It's obvious. But when you extend that out, that reasoning, the math, the thought, the concept out any further than simply a simple up from down determination, it is incredibly flawed. That is what we need to be attacking, people, not whether or not that force is actually there, because it is. But it does not apply. It is a non sequitur to anything other than determining up from down. And that is the position I have had literally since the very first show that Jaron and I ever did together. I said in that show that buoyancy and density absolutely explain everything, but there is still something determining up from down. I have never changed from that position, and I never will, because that's the way it is.
Have you read about the Gestalt experiments when they put the subject with a lens in the eyes that inverts the world, makes the world upside down for the observer? So you put goggles on that invert everything. Suddenly you see everything upside down. And you can look it up if people have studied that. And at first there's a incredible confusion. It is compared to paradigm shifts in a way, but quickly the person readjusts to living with the inverted view somehow.
Yeah, your brain just flips it again.
Somehow flips it, yeah. So that's another interesting thing.
Wizard goggles.
Exactly. So, okay, guys. So that's. Oh, go ahead, UAP.
Well, it's kind of unrelated, but with the mention of wizardry and paradigm shifting and everything, this movie from George Milieu, the 1902 or 03 Fly Me to the Moon or whatever. You know what I'm talking about, with the weirdo face with like the bullet in its eye, the moon.
Oh yeah, yes.
You know what I mean? That really old. It's like the first sci-fi movie, whatever.
Yep, the moon with the missile in its eye or bullet in its eye. Exactly, I know what you're talking about.
Yeah. Well, there's a scene in there where the scientists are getting ready. It's like right in the beginning, and what they're doing is they're formulating their plan of going to the moon. But the scientists, when it starts out, are wizards. They're dressed traditionally like cartoonish, like wizards, with the cloaks and capes, the star and moon patches sewn on, and the pointy hat and the whole get up, magic wands, the whole thing. And they have this meeting, and they draw on the chalkboard a globe, and then they draw the moon, and they draw that orbit thing, the swirly orbit that we've seen drawn even in recent times, like showing how the astronauts got to the moon. And then they have a graduation. They exchange their wizard caps for the what's it called? The mortar. What is it called? The graduation hat. The flat one with the tassel.
Yeah,
and they get those.
Tassel and mortar or something like that. Yeah, I forgot what it's called, but you're right.
Yeah, and they get that, and the black cloaks, just like everybody has to wear. Basically what you're doing when you graduate, you're putting on the modern day wizard garb. Because you have been trained at Hogwarts or whatever school you went to, Princeton or whatever. Yeah. And it's just amazing that they tell you what they're doing right in your face through this like medium of art, and then they do it. And it's just funny that you can see that and not realize or appreciate what it really is saying. And it actually happened, all of it, other than, well, all of it happened because they made it seem like they were going to the moon. It was a stage set and everything, and that's exactly what happened. And it was like the first movies, like that wasn't the only one. There were a whole bunch of them. Edison had quite a few, and they were all like Alice in Wonderland, and then there was moon, like going to the moon. That was like a huge percentage of the very early movies. They even had one to Mars. very early, like 1907 or something like that. But anyway, I just...
What was the one that had the first rocket going up with the countdown? Is that 1910? Is it?
I don't know. They had something akin to like a countdown. It was more of like a shot, like a moon shot, they used to call it, where it's like a barrel of a gun and they send it up. That was the ones that I saw did it like that, but I didn't see a rocket one. So I don't know.
I think it's also early on with the countdown. I think it comes from a film.
Yeah, because it's funny how the countdown thing is so associated with NASA and rocket launches, and you don't normally see adults getting together and shouting out a countdown to something like that.
Unless it's New Year's Eve.
Yeah, it's just not it's kind of a funny thing to do. It's like to dramatize it, but yeah.
Yep.
Yeah, some people say it's the counting backwards, which is a satanic kind of practice. Some people point that out.
Okay.
Inversions.
So let's go ahead and move on from that, and I'm going to cover one more thing before we call it a show. And didn't get a chance to cover this last week, but I thought it was funny. This article here, human missions to Mars will use lasers to communicate with Earth. Okay, now the reason I find this so humorous is...
I need one of those lasers.
Yeah, right?
Yeah, Jaron, you were saying that before, like if you hold it at any appreciable distance, it's just impossible to keep that thing steady.
A nice powered laser going 4 miles, has a beam divergence of like 10 feet. So go ahead and figure that out to Mars, see what the beam divergence would be to cover the entire universe, I think.
Exactly. Well, and of course, they will say that their lasers are way, way, way orders of magnitude better. And of that, I won't dispute. But they are not that much better to the point where they could literally hold a pencil-thin beam going a billion miles away, right? And the other thing that you have to think about this, well, let me read a little bit about this. What this says first. It says, ever since NASA launched the Explorer 1 satellite in 1958, the agency has relied mostly on radio waves to communicate with craft millions or indeed billions of miles across space. But as NASA sets its sight on new destinations for manned missions, it is giving its communication system a much-needed overhaul. NASA is adding a new dish to its deep space network equipped with mirrors and special receiver to allow it to beam and receive lasers from spacecraft in deep space. The new antenna dish, dubbed Deep Space Station 23, DSS-23, is part of a transition to a faster, more efficient communication as NASA prepares for a return to the moon by the year 2024 and sets up for the first human mission to Mars in the mid-2030s. The impetus behind the dish is simple. If NASA is to send humans to Mars, they need to be able to communicate with them, and lasers could help ensure future Martian astronauts have a good reception 40 million miles from Earth. Okay, so...
Did they say impetus or impotence of the dish?
Yeah, well, impotence would be more applicable, I think. But so what they're saying here is that they're constructing this dish that is going to be basically a parabolic optical parabola, okay? And the crazy thing about this is the first thing they say is that it's going to be faster. Well, I'm sorry, but laser light travels the same speed as RF light, so how in the world it could possibly be faster is ridiculous. That's absurd, and it's not true, and it's just a line of BS. Okay? And if there was any difference between EM in the gigahertz range and light, which is in the nanometer range, it would be indistinguishable, frankly. Okay? So that's the first fallacy that they're coming up with. The second thing is they think that by having an optical parabola here, in other words, the concept behind this is that light is going to come into this dish and bounce back through the mirrors to the feed horn or collector point or some sort of an optical sensor, right? And this is going to give them a specific amount of gain to the laser. Well, frankly, I'm still failing to see how it would be any better than RF, but let's continue to look at this. So even if they were able to get a far sharper, more pencil-like beam than they could with a high-gain microwave antenna or anything like that, you still have to take into consideration that when they fire that beam from Mars, you've got at least 4 or 5 minutes of transit time, and during that transit time, the Earth, whipping through at 67,000 miles an hour, plus, ultimately culminating at a 1.3 million miles per hour. And I'm sorry, NASA fanboys, the frame of reference is not going to work here. That's nonsense. It's not going to work. All right. Your receiving station is going to be far out of the optical aiming that's using. So what would they have to do? They would have to then anticipate then where the Earth is going to be, and they would have to constantly make calculations based on that, on multiple different motions, right? So again, and then we have to look at the laser on the transmitting side. Well, what about beam divergence? We all know that there's a huge issue with beam divergence, right? From Jaren's simple laser that he had a hard time keeping a less than a 10-foot diameter over the distance of a couple of miles. Well, even if they use really, really, really good lasers, they're still going to have one hell of a beam divergence going over millions, if not a billion miles, depending on the position of Earth and Mars, apart from each other, right? So we still are going to have beam divergence. We don't really know ultimately where the bulk of that signal is going to wind up. Earth is going to be far away from its initial target length, and they're trying to bypass all of this. I'm sure they're going to say, oh, frame of reference, that'll make it all right, all okay, but it won't, and common sense will tell you that it won't. So
it doesn't make any sense to me anyway. It's just when you look at the laser that they supposedly bounce off the moon, think of the size of that thing, and think of the power. That it doesn't have to have a lot of power to generate a beam like that. I mean, maybe I'm wrong about that, but I mean, a 40-watt light bulb, can just shine in your room. But a 40-watt laser, wouldn't that go through a house?
It would, but it would take a lot more than that to travel 1 billion miles, right?
Right. Yeah, and remember that they claim they communicate with the Voyagers, and that's 13 trillion miles away or something like that. No,
it's not trillion. It's billions, though. It's billions. A big figure.
And so if that's the case, and they do it with the power of refrigerator light bulb with radio, why would they need this laser?
Yeah, right. No kidding. So anyway, I'm just saying that they're trying to come up with something that's new and improved and better, and it's still absurd. Light still has to obey the inverse square law. They don't have enough power out there, anywhere from 100 million miles away to 1 billion miles away. They simply don't, to be able to generate that intense of a beam, to keep it focused. And the idea of focusing it on the receive end through a parabola is just stupid, frankly. It's not going to make that much difference. So I don't see any advantage whatsoever to going laser over RF. In fact, I see a lot of detriments to it. So
with that power, they can cut the Earth in half.
Yeah, that's it. The Death Star. And not only that, then you have refraction problems, that you necessarily wouldn't have. If you're using light or near visible light, what kind of packet errors are you going to get from this journey, this beam divergence, all these other distortion factors that are going to go through? Sure, lasers would work great, in close proximity, and you would probably have a fairly reliable signal. But we're talking about replacing radio frequencies with an optical phenomena that is susceptible to a whole host of other problems. It's just ridiculous again. But this is just another one of those things that, people, the fanboys eat it up. Oh yeah, it's got to be better. We're going to use lasers. Wow, that's space age. So
yeah, I think the reason they're doing it is the amount of data that can be transferred via laser versus whatever they're using now.
Right. Well, yeah, but
yeah, and so they have plans. I think they're actually going to pull off something, some kind of a stunt like they did in 69 through 72.
Right. Well, and I
Yeah.
see what you're saying. They're saying that because of the fact that light is up in the nanometer band, that they can modulate that to a much broader bandwidth. I get that. But again, they've also then gone ahead and introduced, susceptibilities like, refractive problems, light diminishing, when you go at these higher frequencies, the distances diminish. So I don't know. I just see a lot of problems
Yeah, I
with the
agree.
UAP.
It's absolutely impossible. Absolutely.
Yeah, I mean,
but
even if it's possible in a static system, I guess that's what you're saying, right? That it is possible, maybe here on the Earth, to make it faster and so on with lasers and fiber optic or whatnot. But then with all the motion.
I think their plans are such that they're going to have video and different things that are sent that would not be possible with the current usages. So they have to set up this thing through the Deep Space Network, which exists only to be the lone receiver. So it's one of these things where you can't hear it, you can't see it, you can't detect it, you can't pick it up on your equipment. Only the DSN can, and that's why it exists. It's like having Pence audit Trump. It's pointless, but they need to do it.
And beyond that, UAP, think about this. I mean, even that they're using gigahertz microwave signals that are transmitting back, which should be able to easily host broadband video, right? And a huge data spectrum behind it, right? And yet they claim, well, we can't send any video back because we don't have enough bandwidth. It's like, what? So this is supposed to solve that problem? If you can't modulate onto a 2-3 gigahertz or 10 gigahertz microwave carrier enough bandwidth to carry a simple video signal, you got problems. It's just, none of it makes any sense. So anyway.
I just find it pretty hilarious that if they don't even understand the characteristics of light, they could ever efficiently use it to do anything.
Agreed. Absolutely agreed. So anyway, that's all I want to say about that. I think we're going to wrap it up, guys. Karen B had to drop, so thank you, Karen, for coming on with us. And so if there's nothing else with you guys,
I got to run first.
Okay,
Sorry.
so I'll let you close out then. On. You're welcome.
Thanks for having me on, and I'll have a video it's being disputed. If I get it through, I'll post it. But other than that, just working on my book, trying to finish that up as promised. So that's it. Thanks everybody, and we'll see you next time.
All right, sounds good. Thanks for joining us, UAP, and we'll see you later. So let's swing around to Eero. Eero, you want to give us a little quick report on what's going on?
Yes, of course. Recently just finished the conference, so sorry for my absence during the show. I'm started with you guys, and then I need to cut off because I need to drive my YouTube channel with OBS and that kind of technical stuff. But it was really nice. This is the second day. The conference started yesterday. Of course, it's not the type of conference that you maybe think in terms of the International Flat Earth Conference, not that kind of conference. Even it's not the kind of conference that I made anytime that I go to Spain. But it's more, close in terms of the relationship between people. There are people that came from United States. There is a guy, I always forget the name, but he's part of the speakers. He talks about a little bit about the poisons in the food, in the water, and that kind of stuff. And then we have an architect that give some part of the technical stuff behind, at least in terms of perspective. That kind of not technical, but an architect is not the same as a physicist maybe or an astronomer, but it has a very extensive knowledge in terms of the horizon perspective and that kind of thing. We have also talks about history. A lot of guys talks about history. We have we present an experiment with the people that are the behind the art flat, which is our Spanish group equivalent to FA Core, presenting an experiment with a pendulum, but not gyroscope or just a tiny pendulum. I mean a very not super huge pendulum, but a pendulum hanging on the building with 40 meters and trying to detect this motion, supposedly the difference motion between the day and the night with respective to the circle in the sun. And they present all the measurements, and well, of course there is no I'm going to make some kind of a spoiler, but there it's like we are not moving around the sun. So that kind of stuff, and the rest is just in terms of people get together and share information and that kind of stuff. So was a really nice. Was about like 6 hours, and tomorrow we're going to have another 6 hours. So I'm going to transmit tomorrow too. And
Where
that's
is this
it.
going on, Iro?
Excuse me?
Where is it happening?
In Colón. In Colón, Buenos Aires. Yes, the place is called like Columbus. That is the nice thing. So we don't have too much media like we had the last year, but at least we are still doing this kind of conference. So that's very nice.
Awesome. Well, that's great, Iro. So you're going to broadcast tomorrow on it as well. That's super. And maybe you can give us a full report on everything that happened next week. But
yeah, in fact, the guy from United States, he gave the conference in English. There is a woman who translated, but at least that tiny part is in English. I don't know tomorrow what he's going to talk about it. I believe he's going to change the topics, but that part at least is in English. The rest, unfortunately for you guys, is in Spanish, but we can give some kind of report.
Awesome. All right, cool. Well, thank you very much for that report, Iro, and we'll look forward to hearing the rest of it when you get a chance.
Okay.
All right, cool. So let's spin around, I guess, to Rodrigo. What do you got coming up this next week?
Well, just continue what I do. I don't know exactly where. There's so much going on. But yeah, continuing the magazine. There's some people who want to help, some designers offer their help. We'll see if I take that offer and then continue with Spacecrack and the other idea, the Aerius report, right? There's a new one, which it's about a historical sighting of mountains in the distance, and he is reconstructing that in a model and saying at the end, concluding that it's impossible on a ball. So, but he does it in a way that's quite empirical, and since he's been sharing that, I think I'm going to share it with everyone. So it's similar to the first one, if you've seen that. And yeah, thank you for having me, and this has been very instructive. Thanks everybody, Austin and Jaren and Iro. And Karen, who lost her bird. I'm sorry to hear that, Karen. She said she had to go because her bird died for 17 years.
No.
Terrible.
Oh, that's so sad. Charlie Bird is a little cockatiel. Oh man, I'm sorry to hear that.
You met him.
I did meet him, yes. He was a very cute little cockatiel. He couldn't fly, but boy, talk about personality. Yeah, sorry to hear that, Karen. That's bad. So okay. All right. So I guess Austin, you would be up next, sir. What do you got coming up this week?
Just the live streams per usual, and then I'm actually trying to set up a sit down with a couple professors. I don't know if it's going to manifest, so it's just purely just possible. But atom physicist and an astrophysicist, I'm trying to get in the door with a sit down that maybe I can document. Then I have a couple groups of people that are wanting to go out and talk to the public about flat Earth. So those two things are coming pretty soon. But as of now, just the lives, and I'll try and keep everyone updated as I figure those out.
Okay. Beautiful. Well, we'll look forward to seeing that. And I really enjoy your shows, Austin. And I think you and I should definitely, possibly occasionally do a show together, talking about some of the more Ken Wheeler-ish type of things. I think that would be fun. A lot of people have requested that, so I think it'd be kind of a good idea.
Yeah, I agree. I'm definitely down, man.
All right. Sounds like a plan. All right. And last but certainly not least, Jaron, what do you got coming up?
Same old, same old. Raw tomorrow, obviously Thursday with Eru, another lounge on Friday. So, and then also got a video coming out because the Flat Earth, Sun, Moon, and Zodiac Clock app has some new features, and I think only Android is out right now. iOS will be a few more days, I think, and when it's out, David and I will release a feature review or a feature update video. So that should be this week. He's just waiting, I think, for the iOS version to get final approval. And I guess that a few people have already contacted David complaining basically about a subscription pop-up that he added to the app. And the thing is, you can go into settings and then turn off that alert, as far as I know. Again, I don't have the app yet or the new features because I have iOS. So if you don't want to support the app, that's fine. Turn it off. For me, hey, I want to support Dave. I think he does a great job. He did an awesome job with the app, and it's 99 cents. So I'm going to hit subscribe. I won't even notice that I'm subscribing 99 cents a month at all. So it allows him to continue to work on it and pay the bills, basically. He does have to pay like every time he changes anything, obviously. And then also, I think for weather updates, he gets like a monthly bill. So he's in this for thousands of dollars, and basically you could help him out. So long story short, if you don't want to support it, just turn it off. Go into the settings and click, I don't know what the button's going to say. Like I said, I don't have the app. Turn off subscription notification or something. It's meant for those who would like to help Dave and support his work. Maybe I'll be the only one, but I'm okay with giving David 99 cents a month. And if you don't want to, go to settings and turn it off. So that's about it. That video will be coming this week as soon as iOS confirms it. But if you have Android, you've already got it, so you actually would be better equipped to know how the settings work. But I think if you go to settings, there's somewhere that will say turn off subscription if you don't want to contribute.
Yep. Beautiful. Yeah, I'm definitely going to support it.
Yeah, 99 cents. Hey.
Yeah.
Dave does work, and every time he calls and tries to add something or whatever, it's like hundreds of dollars, if not thousands. I don't know. He doesn't tell me the exactitudes of it all. It's his app. It's his baby. It's what he's spent a lot of time on and effort, and the way that you get a video update every day, and the way to keep the video archives, and he does all that work. So he's just looking for, and another thing about David, he's really never asked for anything. So I'm just saying that from a personal standpoint. So if there's some little app way that I can just hit subscribe and 99 cents comes out of my bank account that's tied to Apple or whatever each month, I'm going to do it. But I understand some people out there might be like, I don't want to do that. And that's completely understandable. Just turn it off.
Yep,
right.
Exactly.
Support what you like, or it goes away. That's all.
Exactly. And yeah, I mean, I also know that David asked me to ask the guy that developed the Bob Wins app to make a change to it, and hopefully he'll be doing that soon so it comes up on a specific screen. But he is going to, or maybe he already has incorporated the Bob Wins flat Earth map, the basic takeoff from the null skull map.
Yeah, I think. Yeah.
So yeah, that's going to be on there. So anyway, super. Okay, so yeah, definitely I would support that, guys. It's only $1 a month, no big deal, 99 cents. So I think it's worth it. And coming up next after this show, I believe Crow 777 and Jason will be doing a show. So mods, if you would be so kind as to spam that link, and everybody can run over there and check out Code 777 and Jason Lindgren on their show. They do a fabulous job and a fabulous show. Jaron and I think all of us are big fans and supporters of Crow and Jason. We really like their work, and we think you will too. So coming up immediately after Globebusters, I believe in about 5 minutes, it will be starting. So there you have it, guys. So if there is nothing else, let's go ahead and call it a show. We'll see you guys next week. And thanks for joining us, everybody. Let me check one more thing really quick to do any shout outs. Let's see if there were any additional super chats that I may have missed. It doesn't look like it. I think I got them all. So we will see you guys next week. Appreciate y'all. Love y'all. And thanks for being with us today. Until then, be good to each other. Don't lie to each other. Open your mind because there's truth inside. Peace out, everybody.
Peace.
Peace.